Hi friends, I am Snehal and today we are going to talk about circular motion. So first we'll do some basic definitions and after that we'll do some small derivations in circular motion to get hang of it. So let's begin. So what is circular motion? Yes, of course everybody knows what is circular motion, but let us just define it. So circular motion is motion of a particle along circumference of a circle. For an example, let's suppose we take a stone, we tie a string to it and we whirl it in a circle. Then motion of that stone will be circular motion. Then another example can be given, the motion of earth around sun. Actually it's elliptical, but approximately we can say it is circular motion. Okay. So now let's define some quantities in circular motion. So let me try drawing a circle. Yeah. So let's suppose that we have this particle at this point A and it moves along circumference of this circle. Okay, in anti-clockwise sense. So in some time t, the particle will move from this point A to some other point, let's call it B, and let's suppose this angle is theta. So if we draw a vector starting from the center of this circle to the position of particle, then the angle through which this vector moves is known as angular displacement. Okay, so what is angular displacement? I will call it theta bar. Just to show that it's a vector, I am putting a bar on top of it. So theta bar is angular displacement and it is the angle through which our radius vector moves in some time t. Okay, so notice that I am calling it displacement and not distance. Okay, so just like in linear motion we have displacement which is a vector quantity, in circular motion the angular displacement, which is the angle through which the radius vector moves in some time, it is a vector quantity. So it will have magnitude and it will have direction. Okay, so how do we find magnitude of an angle? So in SI unit, angle is defined as arc upon radius, right? So length of this arc from A to B is suppose S, radius of the circle is R, then the theta is equal to what? S divided by R. Okay, and what will be unit of this? It is radians. Then this is about magnitude. Magnitude we find using arc divided by radius. How to find out direction? So there is convention to find out the direction of angular displacement, and the convention is to use a rule known as right hand thumb rule or right handed screw rule. So what is right hand thumb rule? So here our particle is moving along circumference of this circle in anti-clockwise sense. So right hand thumb rule says take your right hand, curl the fingers of your right hand in direction of motion of particle. So I will take my right hand, curl the fingers of right hand in direction of motion of this particle and stretch my thumb. So my stretched thumb will give me direction of angular displacement, right? So what will be direction of angular displacement? It is outside to the plane of this board. Okay, let's take another example. So let's suppose we have a particle which is moving on this circle. What is this circle? It is in horizontal plane. Okay, so my particle is moving anti-clockwise for me in this horizontal plane. So how do I find direction of its angular displacement? So we have set the rule, it is right hand thumb rule. Take the right hand, move, curl the fingers of the right hand in direction of motion of particle and stretch your thumb. So your stretched thumb will give you direction of angular displacement. Okay, so in this case it was outside the plane of the board. If this particle moved in clockwise sense, it could be inside the plane of the board. In this case, curl the fingers of your right hand in direction of motion of particle and stretch your thumb. So stretched thumb gives upward direction, that means direction of angular displacement is upwards. Okay, so this is how to use the right hand thumb rule. So now we have defined angular displacement, which is analogous to what? Linear displacement in linear motion. So next quantity is angular velocity. Stop.
We can restart now.
Okay. Now let's talk about angular velocity. So just like in linear motion, we define velocity as the ratio of displacement to time. In circular motion, we define angular velocity as the ratio of angular displacement to time. Okay. So what is angular velocity? We'll denote it by this letter. It looks like W, but it's a Greek letter called omega. So angular velocity, omega bar, it's the ratio of angular displacement with time. Okay. So what is unit of angular displacement? It's radian. So unit of angular velocity will be unit of angular displacement divided by unit of time. Okay. So it's radian per second. All right. Then just like in linear motion, we have acceleration, which is change in velocity per unit time. Just like that, in circular motion, we define angular acceleration. It is change in angular velocity per unit time. Okay. So let's define angular acceleration. So what is angular acceleration? Let's suppose at some time t1, the angular velocity is omega 1. What is omega 1? It is angular velocity at time t1, and suppose omega 2 is angular velocity at time t2. Okay. So angular acceleration is denoted by this letter, alpha. And what is alpha? It is change in angular velocity, which is omega 2 minus omega 1 divided by time from t1 to t2. So that will be t2 minus t1. Okay. So it's t2 minus t1. And what will be unit of this? So it is unit of angular velocity divided by unit of time. Okay. So it is radian per second squared. All right. So all the quantities that we have defined till now are average quantities. So all the quantities that we discussed till now are average quantities, and now we'll talk about the instantaneous quantities. So what do I mean by instantaneous quantity? So let's suppose my particle is going around the circle and I want to find out angular velocity or angular acceleration of that particle at a particular moment. Okay, so that's what we mean by instantaneous quantities. All right, so what do we do when we want to find out instantaneous quantities? We take derivatives. Okay, so you must have seen that instantaneous velocity is derivative of displacement with respect to time, or shall we say derivative of position with respect to time. So just like that, instantaneous angular velocity is derivative of angular displacement with respect to time. Okay, so I will define instantaneous. What is instantaneous? It is value of quantity at a particular moment. So instantaneous angular velocity is still the ratio, okay, but it is ratio at a particular moment. So it is omega bar is derivative of theta with respect to time. And similarly, instantaneous angular acceleration alpha bar. So what is angular acceleration? It is change in angular velocity with respect to time. So instantaneous angular acceleration will be what? Change in angular velocity with respect to time at a particular time. Okay. So when we want to find out quantities at particular time, we make use of derivatives. So it is derivative of omega with respect to time. All right. So these are average quantities and instantaneous quantities. Let's stop. Okay, so now let's talk about the relation between linear and angular quantities. So for this particular section, we'll think of these quantities as scalars. So we'll only talk about the magnitude of quantities and not the direction. All right, and I will explain you why. So what is this angle theta? It is angular displacement, but now I am going to call it distance only. Okay, so angular distance theta is equal to what? It's ratio of this arc S with the radius. So if I take r on other side, I will get what? S is equal to what? This r goes on other side in multiplication of theta. So I get S is equal to r multiplied by theta. Alright, so this is relation between the linear distance covered by the particle on circumference of circle and the angular distance theta. Okay, so linear distance is equal to r, the radius, multiplied by angular distance. After that, I will divide both sides of this equation. So let's call it equation 1. I will divide both sides of this equation by time. So S upon T, this is distance divided by time, and it's equal to r multiplied by theta divided by time. Alright, so what is distance upon time? It gives us speed. Okay, so this is linear speed. So linear speed is equal to r times theta divided by t. So what is theta upon t? It is angular speed. So linear distance is r times angular distance. Linear speed is equal to r times angular speed. All right, and then I will find out the relation between linear acceleration and the angular acceleration. But now this linear acceleration, I am going to call it tangential acceleration only, and it's because there is another acceleration in circular motion, and that is called as centripetal acceleration. Okay, so let's suppose omega 1 is angular speed at some time t1, angular speed at t1, omega 2 is angular speed at time t2, and v1 is linear speed at t1, and v2 is linear speed at time t2. So we have just found that v is equal to r times omega. Okay, so I want to find out acceleration. What will be acceleration? It is change in speed divided by time. Alright, so v2 minus v1 divided by t2 minus t1 is my linear acceleration, and what is that equal to? It's equal to r multiplied by omega 2 minus r multiplied by omega 1, and I will take r common, so it will be r multiplied by omega 2 minus omega 1 divided by t2 minus t1. And what is omega 2 minus omega 1 divided by t2 minus t1? It is my angular acceleration. Okay, so a is kind of linear acceleration. It's equal to r multiplied by angular acceleration alpha. But this acceleration a, I am going to call it tangential acceleration. Okay, what is this? This is tangential acceleration, and it happens because of change in magnitude of velocity. Okay, so remember this, tangential acceleration happens because of change in magnitude of the velocity in circular motion. And there is another acceleration called centripetal acceleration, which happens due to the change in direction of velocity. Okay, let's discuss that. Okay, so now let's talk about the total acceleration in circular motion. And this time we'll start with the vector relation between the linear velocity and angular velocity. Okay, so we discussed v is equal to r times omega, right? And what is v, r and omega? So v was in earlier case it was speed of particle. Now I want to talk about vector quantity. So what is the direction of velocity in circular motion? So for an example, you take a stone, you tie it to a string and you whirl it in circle. So if you release it at this point, it will go in this direction. If you release it at this point, it will go in this direction. So the meaning is the velocity is directed in along tangent. Okay, the direction of velocity is along the tangent in circular motion, and that's why we call it tangential velocity. So what will be direction of velocity for this particle over here? So our particle is moving in anti-clockwise sense. So at this point, the velocity will be directed, the velocity will be directed upwards, right? So now, if we talk about vector quantities, so v bar can be equal to r bar cross omega bar, or is it equal to omega bar cross r bar? Okay, so what is r bar? It's a vector directed from center of circle to position of particle. It is called position vector or radius vector, and omega bar is our angular velocity vector. So whether this first relation is correct or the second relation is correct, let's try to find out. And how do we find it out? Using right hand thumb rule again. So how do we find the direction of resultant in case of vector product? We keep our right hand in direction of first vector, we curl our fingers towards the second vector and stretch the thumb. Okay, let's try to do that. So what is direction of radius vector? It is this direction. What is direction of the angular velocity? So as we discussed, our particle is moving in an anti-clockwise sense. So let's curl the fingers of our right hand in anti-clockwise sense and stretch our thumb. So it is outside the plane of this board. Okay, so let's try r bar cross omega bar. So if I keep my right hand in direction of r bar and curl my fingers towards the second vector, which is omega bar, which is outside the plane of the board, I get downwards direction. But is the direction of velocity downwards? No, it is upwards. Okay, so let's try other relation. What is other relation? It is omega bar cross r bar. Let's try this. So omega bar is directed outside the plane of the board and r bar is directed in this direction, right? So keep your right hand in direction of first vector, the omega bar, then curl fingers towards the second vector, the r bar, stretch your thumb. Now my stretched thumb gives me upwards direction. And is it the direction of v bar? Yes. So what does that mean? It means that this first relation is not correct, second one is correct. Okay, all right. So now we got the relation between v bar and omega bar, r bar. Okay, so this one is incorrect, this one is correct. So let's begin with this. So how do we find acceleration given velocity? Okay, let's suppose I want to find out instantaneous acceleration. I take derivative, right? So v bar is equal to omega bar cross r bar, and I will take derivative of v bar. Okay, so on left hand side it is dv bar by dt, and on right hand side I have d by dt of omega bar cross r bar. So notice that we have got two quantities over here. Potentially both of them can change, okay, with respect to time. So we have to make use of the product rule of derivatives. Okay, so let's do that. What is product rule of derivatives? So if you have product of two quantities and you want to find out derivative of that, you have to take derivative of first quantity, keep second quantity as it is, plus keep first quantity as it is and take derivative of second quantity. Okay, So it's equal to d by dt of omega bar cross r bar plus omega bar crossed with d by dt of r bar. Okay, and we'll carry this on the next page. So I will just take this equation from here. Okay, all right, so we got it. This is my dv bar by dt. And now, what is this first term? We have got d omega bar by dt. It is rate of change of angular velocity with respect to time. So it is angular acceleration. Okay. So this first term is angular acceleration cross r bar. And recall, did we discuss this thing? Of course we discussed. This is our tangential acceleration, right? It was r times alpha. Okay. And the second term is omega bar cross g r bar by dt. So what is r bar? It is radius vector, or we can say it is position vector. Okay, because it shows position of particle with respect to center of the circle. All right, so it is rate of change of position with respect to time. And what does it give us? It gives us velocity. Okay, so it is v bar, and this is the total acceleration. And you can see that there are two terms. First term we already discussed. It is tangential acceleration. It is r times alpha. And the second term, omega bar cross v bar, it is called as centripetal acceleration. Why centripetal? Because if you find out direction of omega bar cross v bar using the rule that we just discussed, which is called as right hand thumb rule, keep your right hand in direction of first vector, curl fingers towards the second vector and stretch the thumb. You will be directed towards center of the circle. Okay, that means this quantity has direction towards the center. It's along radius towards the center, and that's why it is known as centripetal acceleration. All right. So the second term is centripetal acceleration. Okay. So what is total acceleration in circular motion? It is sum of tangential acceleration and centripetal acceleration. So I will call it AT bar plus AC bar. Okay, and this is the vector sum. Now if I want to find out the magnitude of this total acceleration, how do I find it out? So we have to make use of the triangle law or parallelogram law of vectors addition. Okay, so this is our centripetal acceleration directed towards the center. Tangential acceleration, if velocity is increasing, it will be directed in same direction as that of velocity. If it is decreasing, then it will be directed in opposite direction of velocity. Okay, so it will be either upwards or downwards. So let's suppose it is upwards. So this is tangential acceleration. How much is angle between them? So angle between them is 90 degrees. All right. So I want to add AC bar with AT bar, and A is their resultant. A is total acceleration. It is resultant of AT bar and AC bar. So the magnitude of A is given by using the triangle law or parallelogram law of vectors addition. Square root of AT square plus AC square plus 2 times AT into AC into cos of the angle between two, right? This is how we find out magnitude of resultant. So it is square root of first vector square plus magnitude of second vector square plus 2 times magnitude of first vector into magnitude of second vector multiplied by the cosine of the angle between two. And how much is the angle between these two? It's 90. And what is cos of 90? It's 0. Okay, so that means we can get rid of this, and we get A equals to square root of at square plus ac square. All right. So this is the magnitude of total acceleration in circular motion. It's what? Square root of magnitude of tangential acceleration square plus centripetal acceleration square. All right. And now let's talk about different forms of the equation or the relation of centripetal acceleration which can take. All right. So now let's discuss various formulae for centripetal acceleration. So one formula is centripetal acceleration is omega bar cross v bar. Okay. And if we just talk about the magnitude, it is omega into what is v? V is r times omega. Okay. So we can say centripetal acceleration is r times omega square. And then instead of substituting v equals to r omega, I can substitute omega equals to v divided by r. So then what will I get? Omega is v upon r, and we have in multiplication we have v, so it is v upon r multiplied by v, so it is v squared divided by r, right? So these are three formulae. One is it is omega times v, second is it is r times omega squared, and third is it is v squared divided by r. So if we want to write it down in vector form, how will it look like? So centripetal acceleration, its direction is along the radius and towards the center of circle. That means it is directed opposite to that of radius vector. So AC bar, if we pick up this relation and put vector, consider r as a vector, so r bar. So I have to substitute this negative sign. I have to put a negative sign. Okay, because the direction of centripetal acceleration and the radius vector, they are opposite to each other. And if I take this relation, so AC bar equals to magnitude is v square upon r. Just to show direction, I will put a unit vector in direction of radius vector, but the direction of centripetal acceleration is opposite to radius vector, so I have to put a negative sign. Okay, so these are vector relations for centripetal acceleration. Okay, so that's all for this lecture. See you in next lecture.